In the last lecture, we talked about how three variables manifest themselves in experimental data. And the idea there was that you would be able to look at experimental data and from that data determine whether you were reaction limited, external mass transport limited, or internal mass transport limited. So the first thing we're going to do today is put that thought process to the test, okay? And we're going to do that with an example from your book. And the example has some data here to the right for this overall reaction where A goes to B, and it's happening in a packed bed reactor. And so then we're supposed to figure out when the reaction is controlled by each of those three regimes, and then also to ask whether or not it's possible to use the plot to determine the internal effectiveness factor and the total effectiveness factor, okay? So to do that, I'm gonna go back to this table for just a second that I was showing. And one of the things that we wanna remember here is that when we are reaction limited, essentially the only variable that plays any role in the behavior is the temperature, right? Nothing else really affects the reaction. When you talk about external mass transport control, everything has a little bit of an effect. That the flow rate has an effect, about the flow rate to the 1/2. The particle diameter has an effect. The temperature has a linear dependence. And when you're internal mass transport limited, the flow rate has no effect. The particle size does. And we are also exponentially dependent on temperature. And we showed why in the last lecture. So there are a couple of things to note here when we want to think about regimes that have control inside of our data set. So here, notice we're only changing two of the variables in this problem. We're changing temperature as we move from the left to right in this plot, and we're increasing the flow rate as we go from the bottom of the plot to the top, okay? So when it comes to this table that we looked at last time, we're not looking at this, right? We're only looking at the effect of flow rate and the temperature. Now, if we want to see something that's sort of interesting here, that when we're not considering the particle size, actually the reaction and the internal mass transport have the exact same dependence on flow rate and temperature. So discerning between those two is going to take a little bit of, I guess, engineering intuition, and we'll get into that in a minute. The other thing that's really noteworthy, I think, is that there's only one thing in this table that has a linear dependence, and that's external mass transport. So one of the things that we can do immediately when we look at this data set is we can look at where the data set is linear. And anywhere that that data set is linear, we know that we are limited by external mass transport. So let's actually label that as external mass transport controlled. And I'm going to do that in blue. So we're going to say that when we have blue, we are dominated by external mass transport. And that's where it's linear, right? So here and here. Right? So one of the interesting things in this plot is that at very low flow rates, this 10 gram mole per hour, we know that we are always external mass transport limited. And maybe that makes some kind of sense because, or at least at this range of temperatures, because if internal and external mass transport and reaction all are going to play a role somewhere, the lowest flow rate should have the most significant effect on external mass transport. Okay, so maybe that makes some kind of sense. Now, when we get above this flow rate, that's 100 gram moles per hour, there's something else that takes over. And that something else has, an almost exponential dependence. But if you look at the lower temperatures, that also has some sort of exponential dependence, right? And of course, I'm looking in this regime and I'm looking at this regime, because from both of these, I could see myself saying, well, that's kind of an exponential. You also could say that that's kind of an exponential. Now, it's not plausible in a reacting system that, let's say, you would be kinetically limited, then go through some mixed control, and then be kinetically limited again. So one of the things that we're going to know is that one of these exponentials here is going to be controlled by the external mass transport, and one of these exponentials here, and I'm sorry, I'm not going to use blue again, is going to be dominated, or its behavior is going to be dictated by kinetics, right? So one of these is kinetics, one of these is external mass transport. And here's where I said that our engineering intuition is going to come into play. So let's think about what would happen as we went to the lowest possible temperatures. So even if we were at the point, let's say, just above freezing for the solvent, right? Mass transport would still happen. But if you got really, really cold, the reaction would stop in its tracks. So at the lowest temperatures, we are kinetically controlled. So that should be kinetics, right? Kinetic control. And at these very, very high flow rates and higher temperatures where the reaction rate should have gone up, we should have internal mass transport control. Okay? And so when you look at experimental data like this, that is one way to think through the problem. And the other thing that validates the fact that internal mass transport is controlling here, right, of course, is that the flow rate doesn't have an effect. Of course, it wouldn't have an effect on the kinetics either. But that's just another validation, I think, of the thought process. So before I do anything, to be more quantitative about this, I want you guys to have the opportunity to ask any questions that you have. So does anybody have a question about the thought process here?
I have a question for like the 100 gram mole per hour flow rate. Could you maybe on that like bin that happens?
Yes, yeah, that's a really great question. So one of the things that's going to happen is that as we manipulate variables inside of our reacting system, you're going to transition between different types of control. So when I look at the 100 gram mole, what I see is that, we said in this range here, we're kinetically controlled. And then we said whenever that you're linear, you're external mass transport controlled. So that is my belief of what's happening here, is that you're kinetically controlled here, and then you transition to external mass transport control as the rate of mass transfer has to increase, right? Because the rate of reaction is increasing over time. And so it becomes the external diffusion that starts to limit the reactive behavior. And at the higher flow rates, you're going to kinetics, then to internal mass transport. And you're able to skip the external mass transport limitation because the flow rates are already super high. Okay, does that make sense?
Yes.
All right, great. All right, so let's take another look at this data set and answer this last question. Can we use the data to determine the internal effectiveness factor and the total effectiveness factor? Now, that question in and of itself, quite honestly, is a little bit of a trick question, because those effectiveness factors are a function of all of the variables, right? And in all the math that we've done so far this semester, hopefully that comes out, that we know that as you're changing the temperature, you might influence the kinetics and the internal mass transport. But by saying that you influence internal mass transport means you're going to change the internal effectiveness factor. So what you need to be able to do is use the data set to find the effectiveness factors at a given operating point. Okay, so let's do that here. Let's find those for very specific locations. So let's first start by finding the overall effectiveness factor and the internal effectiveness factor at, let's say, 360 Kelvin. And the reason I picked that is because it has this really interesting like hitch here. And when you get to higher flow rates, right, you essentially have, you know, when you go from 100 to 1,000 to 5,000, you really have no change there. And so it's a really interesting, to me at least, it's a very interesting point. So let's think about this just a little bit. And let's look at the overall effectiveness factor. And if you remember, we actually defined the overall effectiveness factor as the rate of reaction divided by the rate of reaction if everything was at the bulk concentration, right? All right. And so if that's the case, well, when would we have everything at the bulk concentration of A? Well, the bulk concentration of A is when you're kinetically controlled, right? Or that that the concentration of A is equal to the bulk everywhere when you're kinetically controlled. And we said a moment ago, that's this area on the plot. So one of the things that we could do is we actually know what the kinetic rate is here, right? It's that dot. And I'm going to eyeball this, right? This is about 0.7, okay? Now, for the flow conditions where FT0 is equal to 100 gram mole, and when you're at 1,000 and 5,000, the effectiveness factor, the overall effectiveness factor is about 1, right? It's approximately equal to 1. But as we decrease the flow rate, we know that external mass transport takes over. And so here, at 10 gram mole per hour, we're going to say, I'm going to eyeball this as like 0.25, right? It's pretty close. And so we actually could calculate at 10 gram mole per hour and 360 Kelvin. Under that condition, we could find the the overall effectiveness factor, which would equal 0.25 over 0.7, right? And that's like 0.37, right? And so we were able to use the data here to calculate the overall effectiveness factor. Now, we could pick another, or I guess we also could look at the internal effectiveness factor, which we actually defined as our rate of reaction over our rate if the concentration of A equaled, or the concentration of A in the pellet was equal to the bulk concentration, right? So at the surface, right? So if we look at this at our condition at 100 gram moles, or even at 10 gram moles, actually, if we think about this, we're external mass transport limited down here, and we're kinetically limited here. So actually at both of those locations, that is approximately equal to 1. Because the bulk concentration, or the concentration, I apologize, that the concentration in the particle should be equal to the surface concentration, because we're not internal mass transport limited. Now, because that's the case, let's pick a location where maybe that's not true. So let's do this. Let's move a little bit positive of that, and let's say at like 365. So let me see if I'm capable of drawing something like a straight line here. And maybe 365 is not exactly the right place, because that's in the mixed control region. So let's go here. Let's do this. let's draw a straight line, a straight-ish line to here, okay, at 370. So now let's actually have a look at the internal effectiveness factor at this place, right, at high flow rates, let's say 1,000 gram moles per hour. Well, to do that, we have to figure out the rate of reaction here. And to do that, right, we'll go here and we'll go sideways and we'll call this like 1.25 approximately, okay? Now we have to figure out what the rate of reaction would be if we followed our exponential. And so now we're here, right? And we're going to go up. And we are going to cross over here. And we're going to go here. And that is something like 1.7. And again, right, I'm just kind of eyeballing this. And 1.25 over 1.7 is something like 0.7. Okay. So we could use the data here to calculate our internal effectiveness factor and the overall effectiveness factor for the process. Okay. All right. Does this last part make sense to you guys?
Yes.
All right. Perfect. Great. That's good to hear. You guys will get some practice doing this on the homework as well. Okay. So then we have a second example that we're going to solve today. This one is also integrated with your homework. It is also it is by some margin the most complicated example problem that we've solved in class, which is also one of the reasons why it's the first homework problem. Which if you guys looked at, you thought, I don't know what to do. That's okay. That's what class was going to be for today anyway. So we're going to solve example 15B from Fogler 5th edition. And I like this problem a lot because it really does combine all of the stuff that we've done for the last few weeks. It's everything all wrapped up in one problem. And that problem says in section 7.14, we saw that nitric oxide plays an important role in smog formation, and there are great incentives for reducing its concentration in the atmosphere. It is proposed to reduce the concentration of NO in an effluent stream from a plant by passing it through a packed bed of spherical, porous, carbonaceous solid pellets. A 2% NO, 98% air mixture flows at a rate of 1 × 10⁻⁶ cubic meters per second, or basically that's 1 milliliter per second. And through a 2-inch ID tube packed bed or with porous pellets at a temperature of 1173 Kelvin and a pressure of 101.3 kilopascals. So here's the reaction. NO plus carbon gives you CO2 plus nitrogen. Calculate the weight of catalyst necessary to reduce the effluent NO concentration to 0.004%. It might not look like such a complicated problem, but it is. And because of that, we're going to step through this step by step. Okay. Now, the first thing that I like to do is I want for us to figure out what we're going to need to calculate, what parameters. And if you remember, we went all the way back at the beginning of the semester and said, what is the first thing that you do? Right? It's write the rate law and complete the mass balance. We're going to do that here as well. And when we do that, we know that DFA, DV, and I'm going to start as a PFR on purpose, because we said in the last lecture that was equal to we know that's equal to the rate of reaction. And in our last lecture, we knew that then is minus the overall effectiveness factor times CA, okay? And I wanted to leverage this relationship that we derived last time. Now, our problem asks us to introduce the weight into this problem, right? And if you remember, right, this is DFA over D weight times the volume over the weight, right, is equal to minus that stuff on the right-hand side. And that thing is just rho B, right? So then this simply becomes DFA dW times rho B equals minus the overall effectiveness factor times K1 times CA. And then this becomes DFA dW equals minus the overall effectiveness factor times K1 prime times CA. Okay, that's good. Now, our next instinct here, based on what we've done this semester, is to make substitutions for the concentration, right? And when we do that, we know that this is D times CA times V dW is equal to minus that stuff that's on the right-hand side here. Now, this is a really interesting problem, to me at least, because most of the time here, this would signal to us we need to say, well, FA equals FA naught times 1 minus the conversion, and CA times V equals CA0 V0 times 1 minus X, and then CA equals then CA0 times 1 minus X times V0 over V. Now we're isothermal and isobaric, so this just becomes 1 plus epsilon X. And that's fine. Actually, that's a totally acceptable way to solve this problem. But I noticed something, and so did the people in the book, that's really interesting. Let's look at epsilon here. So epsilon, we know, of course, is just the mole fraction of A times the change in the number of moles divided by the absolute value of the stoichiometric coefficient for A. Well, what is YA in this problem? Well, let's go back to the problem statement. It's 2% NO. Well, 2% NO tells us that that is 0.02 times delta N. And if you remember, our reaction was NO plus carbon gives us CO plus 1/2 nitrogen. And so we have 2 goes to 1.5, right? So that's minus 0.5 divided by 1, right? And that number is negative 0.01. That's really small. And that essentially means if you went to full conversion, you would change the volumetric flow rate by like 1%. So the simplifying thing here is that, again, this is like an engineering simplification. When epsilon is equal to that value, they say, you know what, that just means that that is approximately constant. Okay? And if that's approximately constant, and here I'll actually complete that by writing the approximately sign, we'll just pull it out of the differential. There's no sense doing all that math if we don't have to. And so the simplification here is not necessarily to change everything in terms of conversion, but to realize that the volumetric flow rate is around a constant. And so that becomes the volumetric flow rate times dCA dW. And I'll put the 0 there just to have it for the initial, so we remember. And that's minus the overall effectiveness factor times K1 prime times CA. And then finally, you get to this place where dCA dW equals minus the overall effectiveness factor times K1 prime over V0 times CA. Okay. Now, there's one more substitution to make here. And when you guys go and look at the problem, when we solve it for the homework, one of the things that you're going to notice is that they give you K1 double prime, right? They give you this. They don't give you this. And if you remember from what we did in our previous lectures, K1 prime just equals K1 double prime times the surface area, right? Times SA. And so we're going to make that substitution. So we get dCA dW equals minus the overall effectiveness factor times SA times K1 double prime over V0 times CA. Okay. And let's divide by CA and multiply through by DW. So we get DCA DW, or sorry, DCA over CA, I'm sorry, is equal to minus the overall effectiveness factor times SA times K1 double prime over the initial volumetric flow rate times D. And we're going to integrate that, right, from CA0 to CA, and we're going to integrate that from 0 to W. And when we do that, we know that the left-hand side, because we've done this several times before, is just the natural log of CA over CA0, and that equals minus the overall effectiveness factor times SA times K1 double prime over V naught times the weight. And the thing that we're asked for in this problem is the catalyst weight. So the weight is then just equal to minus the volumetric flow rate divided by the overall effectiveness factor times SA times K1 double prime times the natural log of CA over CA0. Okay. And that is what we're after. Okay. Now, this might look very straightforward, but here's where the problem actually becomes complicated. That we have this functional form. We actually know what the final concentration is going to be, right? We want it to be 0.004%, and we know the initial is 2%. We're given SA in the problem. We're given K1 double prime in the problem. We can find the volumetric flow rate. In fact, the volumetric flow rate's given. So then the entire crux of this problem is in determining this, right? It's in actually figuring out what the overall effectiveness factor is. And that's what we're going to spend a lot of the time doing for the rest of the lecture today. Now, if you remember, in our last lecture, we had a definition for the overall effectiveness factor. And we said that that's equal to the internal effectiveness factor divided by 1 plus the internal effectiveness factor times K1 divided by KC times AC. Okay. Well, this is where the problem blows up a little bit, because now we have a bunch of new things to find. So we need to calculate this and this. Okay. And in fact, we also need to calculate this and that. So we have to calculate all 4 of those things. Now, the last two, KC and AC, I'm going to just give you guys the values when we need it, because we've already done examples in homework 6 where you did that. And you'll get practice doing that again here. And plus you have the book to guide you. So I have a little bit of confidence that you guys can already calculate those two. So I want to focus on the calculation of those. Now, the easiest one for us is K1. Okay, so we already know that K1 is equal to K1 times rho B, which we already took advantage of as we started to solve this problem. And we also made, K1 prime times rho B. And then we also made the substitution to introduce the surface area, right? So this is just K1 double prime times rho B times SA. Another substitution that we've had previously, and it's something that we'll need in this problem, is that they don't actually give us rho B, they give us rho C, which is like the bulk density. And that is equal to rho B times, or sorry, I actually wrote this backwards. That rho B, I apologize, is equal to the bulk density minus or times 1 minus the porosity. So actually this thing becomes K1 double prime times rho B rho C times 1 minus the porosity times the surface area. Okay. And you guys,
I have a question right here. Can you hear me?
Yes.
Okay, perfect. So I thought B was like the density B was the bulk one, and then the C was the pellet. Or
So
am I?
so row B is, oh, okay. That's a good correction. So row B is basically the weight of the catalyst per volume of the reactor. And then row C, yeah, I see your point here where I think we said the same thing. I just might have misspoke slightly. And rho C is the catalyst density. And then the 1 minus theta is the bulk porosity, not the particle level porosity, but the bed level porosity. And so yeah, rho C is the density of the catalyst, then times 1 minus the bulk porosity, which gives you the overall rho B, which you're calling the bulk density. So yeah, I think we have the same understanding, but that was a really good point to bring up. Yeah, that's very good. Because you're right that this rho C already takes the porosity of the pellet into consideration, right? Where this is the porosity of the bed. Great question. Actually, that was a very good question. So thank you for coming in and interrupting that. That was more than worth it. So thank you. All right, so let's calculate this. So we're given K1 double prime in the problem. So this is 4.42 times 10 to the minus 10 meters cubed per meter squared seconds. And then we have rho C, which is given in the problem as 2.8 times 10 to the 6th grams per cubic meter, times 1 minus the porosity of the bed, which is 0.5, times the surface area, which is 530 meters squared per gram. Okay, and so now we can find the value for K1. Okay, so K1, if we just want to look here for a second, so the cubic meters will cancel, grams cancels, meters squared cancels. So we're going to get something that's just inverse seconds. And this is 0.325 inverse seconds. Good. All right, so we got K1. So that's great. Now we're going to calculate the internal effectiveness factor. And to do that, we're going to use a formula that I showed last time, but not one that we've actually done a calculation with yet. And that was that the effectiveness factor was 3 over the Thiele modulus times the square root of the Thiele modulus times the hyperbolic cotangent minus 1. Okay. And if you remember, since we have a first order reaction here, that the Thiele modulus for our first order reaction was equal to the radius of the pellet squared times this thing that we called K1 prime divided by the effective diffusivity. And the reason that we had defined this as K1 prime is because it differs from K1 slightly. So in our previous work, right, K1 prime was equal to K1 double prime times rho C times SA. And the difference here between K1 prime and K1 double prime when we were looking at the Thiele modulus was that K1 has, and maybe here's a better way to show where it is, has rho B in it, not rho C. And so when you're calculating the Thiele modulus, this is the definition that we made in this thing that we called K1 prime. So that's something to be very careful about, okay? So now to do this, we have to actually calculate K1 prime, or K1 star, I apologize. And so that K1 star is equal to those two things, which again is 4.42 times 10 to the minus 10 meters cubed per meter squared seconds, times rho C, which is just 2.8 times 10 to the 6th grams per cubic meter, times the surface area, which is 530 meters squared per gram. And that should just be twice the value of K1, right? Because you're just taking the bed porosity out of this. And that is 0.66, okay? Inverse seconds. Okay. All right, so now we can actually go about the business of calculating the Thiele modulus, okay? So then that squared equals, if we look at the radius of the pellet, well, we're told the diameter, so we can actually just convert that into the radius, and that's just 3 times 10 to the minus 3 meters, right? And that's squared times this K1 star divided by the effective diffusivity, which is 1.82 times 10 to the minus 8 centimeters squared per second. And so we get a Thiele modulus that's equal to 324.6. And then we also need the square root of the Thiele modulus, which is 8. We'll call that 18. Okay. And so then we put this into our equation here, and you'll find that this is equal to 0.157 when you guys do this. Now, one of the things that I want to note here is that the book actually doesn't follow their own rules here. So they give a simplification that when this is greater than 20, that you can simplify this to simply be 3 over the square root of the Thiele modulus. Now, this is not greater than 20, but they use that simplification anyway, which I didn't do. So my value here is 0.157. Theirs in the book is 0.167, and that's very simply because they didn't follow their own rules. Okay. Now, to find AC, right, this last 2 parameters that we need here, AC and KC, just to point you in the right direction, remember AC here is equal to 6 times 1 minus theta over the diameter of the particle. Okay, and you should get a value of AC of 500 inverse meters. Okay, and from KC, right, you're going to find KC the same way that you've done before, right? We know that the Sherwood number is going to be like the Reynolds number to the 1/2 over the Schmidt number to the 1/3. Okay, and it's 1 times that number in our bed. And from that, right, you have the particle diameter. All those variables are still in there that you guys have had practice with already. And so that's going to be like 6 times 10 to the minus 5 meters per second as that mass transfer coefficient. Okay. So now we have all the information that we're going to need to calculate our overall effectiveness factor. Okay, so I'm going to just copy this down here. And that is then equal to 0.157 divided by 1 plus 0.157 times 0.325 inverse seconds divided by 6 times 10 to the minus 5 meters per second times AC, which we already said was 500 inverse meters. And that gives us an overall effectiveness factor of 0.058. Very low, right? 1 would be great, right? 1 means that we're taking advantage of all of the internal and all of the external surface area, which clearly we're not doing. And we're going to revisit this in just a minute. Now, fortunately, we have everything that we need now to solve this problem, right? We said that weight was minus the volumetric flow rate divided by our overall effectiveness factor times K1 double prime times the area. And we're given in the problem that, oh, sorry, I forgot the natural log term, times the natural log of CA over CA0. All right, so we're given the flow rate in the problem, right? And that is just 10 to the minus 6 cubic meters per second. And I just made sure that the units all worked out. And this is 0.058 times K1 double prime, which is 4.42 times 10 to the minus 10 meters cubed per meter squared times seconds, times the surface area, which is 530 meters squared per gram, times the natural log of 0.004 over 2. right? Because we're going from 2% to 0.004%. So now let's do this calculation, and the weight, if we just make sure that all the units cancel, right? So meters cubed cancels, seconds cancel, meters squared will cancel. That means the only thing that's left is 1 over grams. And so the units are going to be in grams, and that's 456 grams, which again is slightly different than what the book shows. And that's because their internal effectiveness factor value was different because they made that incorrect substitution. The last thing that we could do as well is we could calculate the reactor length if we wanted to. And we know in our system, right, that the weight is equal to rho B times AC times the length, right? And if we do that, then that is simply, well, I guess we'll rearrange this, and the length is equal to the weight over rho B times AC. So that would be 456 grams divided by 1.4 times 10 to the 6th grams per cubic meter times 2.03 times 10 to the minus 3 meters squared, right? Using the diameter of the pipe that we have. And that gives us a length of 0.16 meters, which is the same value that the book had. Okay, so here's our problem. I know that we skipped the complexity of KC, AC. That'll add a little bit of time, but I wanted to give you guys the values. And like I said, you guys have had practice with this. Now, before I talk some more and maybe point out one more additional thing, does anybody have a question about what we did in going about solving the problem? All right, if not, so now that we have this, I really want to talk a little bit about what the values mean for the internal effectiveness factor and the overall effectiveness factor. So one of the things that we would think about is that if the internal effectiveness factor is about 1, that means that you probably don't have any internal mass transport limitations, right? But if it's less than 1, you certainly do, right? That means that you have, internal mass transport limitations, right? And here in our problem, this was equal to 0.157. So obviously, we have some issue. The other thing is that if you look at how we calculate the overall effectiveness factor, the overall effectiveness factor can never be less than, can never be more than the internal effectiveness factor. And so a good criterion to look at is if the overall effectiveness factor is less than the internal effectiveness factor, then you have external mass transport limitations as well. And in this problem, our value for the overall effectiveness factor was 0.058, which is about a third of the value. And so obviously in this problem, we have both at hand, right? We have both internal mass transport limitations and external mass transport limitations. Now, this is sort of hand waving. There are much more formal ways to do this. So when we talked about internal diffusion, we used this equation already, that the effectiveness factor was 3 over the Thiele modulus times the Thiele modulus, or the square root of the Thiele modulus, times the hyperbolic cotangent of that minus 1. And the effectiveness factor is essentially unitless. So what some people will do is they say, hey, look, let's just multiply by that, right? And get this 3 times this times the hyperbolic cotangent minus 1. And that essentially gives us some measure of the reaction rate over the diffusion rate, because we have the Thiele modulus here multiplied just by some factor with no units, right? And so in the book, they talk a little bit about the Weiss Prater correlation. And what they say is that if this value of the Thiele modulus times the effectiveness factor is less than 1, you have no internal mass transport limitations. But if that value is much greater than 1, you have what they call significant mass transport limitations. And now if we actually look at that, remember the Thiele modulus in this problem was 324, if I remember correctly, and our internal effectiveness factor was 0.197. So if you take the product here, that product is equal to 51, which is much greater than 1. So obviously we have significant internal mass transport limitations. So that's for internal mass transport. For external mass transport, there's also the Mears criterion. And essentially what the Mears criterion is that they derive this expression that minus RA prime, right, the observed value for the reaction rate, times rho B times R times the reaction order, N, divided by Kc times Ca, right? And of course, capital R is the particle radius. And what they say is if this thing MR is less than 0.15, you can neglect external diffusion. And so we can do a little bit of a simplification here because we know RA prime is actually just equal to the overall effectiveness factor times K1 prime times Ca, right? We had that earlier in our problem. And so if that's the case, MR then is the overall effectiveness factor times K1 prime times Ca times rho B times the radius times the reaction order over Kc times Ca. And the Ca's, of course, just cancel. And we can calculate this value. And if we do that in our problem, that is equal to 0.97. And obviously, then it doesn't satisfy that as well. And as we ended here, I just wanted to bring that to your attention that, we can have a hand-wavy type argument, which I think works well. And there's some understanding in this based on what we've done before. But there are more formal ways to do this, whether it's this correlation or another one, whether it's this correlation or another one, but they do exist. And for some of them, whether you have experimental data and then you're able to calculate the effectiveness factors in certain regimes, if you wanted to do then model, if you wanted to do reactor modeling, you actually could know from the experimental data how complicated that model might have to be. You also could know some of these values up front and then also be able to develop your fundamental equations, knowing at the beginning whether you're internal and external mass transport limited or not. And if you knew some of these criterion, then you might even be able to get all the way back to dFA dW just equals K1 times Ca and not have to take any of the mass transport into consideration. But that's the framework that we've tried to develop over the last several lectures. And hopefully now this problem brings it all together.